Hey guys, welcome back to Unacademy CUET English. This is Aaqib Mubashir, your physics educator. I hope you are all keeping well back at your places. Guys, in this particular session, we are going to talk about one of the most important topics of your electrostatics, that's capacitors. So without wasting any time, let's get started. Guys, in electrostatics, we have dealt with one of the topics called as properties of conductors. In that particular topic, we discussed that when we give charge to a conductor, the conductor stores that charge on the surface. The charge never penetrates into the bulk, right? So later on, we will get to know that when conductor stores charge, it actually stores the energy. So that means we conclude that conductor has a property of storing charge and in turn energy. Now this property of the conductor is what we call as property of capacitance. So that means this capacitance, which is a property of conductor, right? It's actually the property of storing charge and energy. Property of storing charge and energy. Guys, this is the property which we are going to explore and understand in this particular topic, right? Now, our actual job is to find what is the capacitance of different capacitors or conductors, right? Now, that is actually the job and that's actually the task to be understood in this particular session, right? In electrostatics, we know that when we give charge to a conductor, potential is developed on the surface, right? So what will be the potential on the surface? That depends on how much charge you have given to the surface. So that actually means the potential of the conductor is proportional to the charge given, right? More the charge given, more is the potential that's developed on the surface. When you remove the proportionality here, you get the proportionality constant V is equal to 1 by C into Q. Now this C is what we call as capacitance. This is what we call as capacitance. So from this equation, we get that your C is equal to Q divided by V. Right? Now this is the equation which is very important for us in this particular session, right? Now, when you have a first look at this equation, you'll see that your capacitance of a capacitor is directly proportional to charge. It's inversely proportional to the potential or potential difference, right? But guys, that's not true. The capacitance of a capacitor does not depend on the charge of the capacitor. The capacitance of a capacitor does not depend on the potential of that particular capacitor, right? So the question is then, sir, what this equation then talks about? Guys, let me tell you that this equation is a working rule actually, how to find the capacitance of a capacitor. And what exactly that means? That actually tells me that if you want to know the capacitance of a particular capacitor, you got to give the charge and check the potential or potential difference, make a ratio, you get the capacitance of that capacitor. It does not depend on charge. It does not depend on potential or potential difference. This is just a mathematical equation to find out, to calculate the capacitance of a capacitor. Now the question is that, then sir, what are the factors this capacitance of a capacitor depends on? Guys, there are two factors actually. There are two factors actually your capacitance depends on. Two factors. Number one, it depends on the geometry. It depends on the geometry of the capacitor. What exactly that means, geometry of the capacitor? It sometimes means the radius of the capacitor. Sometimes it means the area of the capacitor. Sometimes it means the distance between the two conductors. Now these are the parameters which we call as geometry actually, and these are the parameters your capacitor actually depends on. That's number one. And number two, it depends on is medium. It depends on medium. These are the two factors your capacitor capacitance depends on. It does not depend on the charge. It does not depend on the potential of that particular, potential difference of that particular capacitor. Right? So that is the working rule for us. This equation is actually the working rule for us. That if you want to know the capacitance of a capacitor, I'm repeating this, that you got to give the charge, check the potential or potential difference, make the ratio, you get the capacitance of that capacitor. Right? Now let's see how exactly we are going to use this particular equation. And for that, I will take my first example. I want to know that what is the capacitance of an isolated spherical conductor. Spherical conductor. Like this. Have a look here. Suppose that we have a spherical conductor here, whose radius is, let's say, equal to r. I want to know that what is the capacitance of this isolated spherical conductor. So as the equation is with us, that your C is always equal to Q divided by V. So what I have to do is, I have to give charge to this capacitor, or I have to give charge to this isolated spherical conductor, check the potential, make the ratio, you get the capacitance of this isolated sphere. Right? Let's do it. Have a look here. Let's assume that I give it charge Q. I give charge Q to this isolated spherical conductor. So because of that, a potential will be developed on the surface, and that will be equal to gamma Q divided by R. Gamma Q by R. Why this gamma, you all know, is equal to 1 by 4 pi epsilon naught. So what I did here is that I give charge Q, I check the potential. So I have potential, that's gamma Q by R. Now I need to know, and I need to find what will be the capacitance of this isolated spherical conductor. So we know that C is equal to Q by V. So my C will be equal to the charge given is Q, and the potential that's developed on the surface is gamma Q by R. So I will write here gamma Q by R. R will come in the numerator. So this Q and Q will go, all what you get is R by gamma. Why this gamma is equal to 1 by 4 pi epsilon naught. So when I put the value of gamma here, your C comes out to be 4 pi epsilon naught into R. And this is what is the capacitance of an isolated spherical conductor. That's 4 pi epsilon naught R. Now that actually tells you that this C equal to Q by V is actually a working rule, a mathematical working rule to find the capacitance of a capacitor, or to find the capacitance of a conductor. And the capacitance of an isolated spherical conductor is 4 pi epsilon naught R. Now having a look at this equation, now it demonstrates, it again tells you same two things. That the capacitance of this isolated spherical conductor depends on geometry, because you can find R here. It depends on the radius. That means it depends on geometry. It depends on medium as well, because there's epsilon naught here. Because if you change the medium, the value of epsilon will change. So that means the capacitance of a capacitor indeed depends on two things. One, it depends on the geometry, and two, it depends on what we call as medium. That was my example number one. Example number two. Let's say that I want to know the capacitance of a spherical capacitor. Capacitance of a spherical capacitor. Have a look here. Let's assume that I have a spherical shell here, like this. I have a spherical shell. Let's assume that the radius of this spherical shell is A. I take one more concentric spherical shell here, whose radius is, let's say, equal to B. I want to know the capacitance of this spherical capacitor. So what I'm going to do here is, I will give charge to the inner sphere. This charge will reside on the outer surface of this inner sphere. And because of induction, minus Q will be developed on the inner surface of outer spherical shell. Since outer spherical shell is electrically neutral, so plus Q will be developed on the outer surface of outer spherical shell. But what if I earth this outer sphere? I will earth this outer sphere. I will connect it with the ground. So when I earth this outer sphere, when I connect it with the ground, because of that, what will happen? The potential of this outer sphere will become zero. So VB will become zero, right? And that will become zero. You must have heard about it. You must have discussed about it in your what we call as electrostatics. And how that potential will become zero, this plus Q from here will actually get transferred to the earth. So the charge on the outer surface of the outer sphere will be zero. It will be, the charge on the outer surface will be zero, right? And the potential of this sphere will become zero. So that is that the point now is that I give charge to this spherical capacitor, charge Q. I earthed this outer sphere. The potential of the outer sphere becomes zero. Right? Now the job is to find the potential difference between these two spherical shells. Right? I want to know delta V. And that will be obviously equal to VA minus VB. Now I don't need to calculate VB because VB is already zero because I have earthed the outer spherical shell. I need to find VA. Now have a look here. How to find VA? Again, this is something which we have already done in electrostatics. Now, if you want to know the potential at this point, that's a VA, there'll be the potential because of two charges. One, the charge that lies on this inner sphere, that is charge Q. And one, the charge minus Q, which lies on the inner surface of outer sphere. Right? And I'm sure that you will be able to understand it because you have already discussed this in electrostatics, that the potential at A or the potential of the inner sphere will be gamma Q divided by A. This is the potential due to this charge Q, and minus gamma Q divided by B, and this is the potential due to this minus Q which is on the inner surface of outer sphere. So that means the potential at A will be equal to, if I get gamma Q common outside, I will get 1 by A minus 1 by B, and that will be B minus A divided by AB. So I got VA. So when I got VA, I can easily calculate what will be the potential difference. That's equal to VA minus VB. Since VB is zero, so potential difference will be only equal to VA. So it will be gamma Q divided by B minus A divided by AB. So this will be the potential difference between these two concentric spherical shells. So I gave charge Q, I checked the potential difference. Now it will be easy for me to know the capacitance of this spherical capacitor. How exactly? For that, I'm going back to the equation that C is equal to charge given divided by potential difference. Remember that. It is charge divided by potential sometimes. It is charge divided by potential difference sometimes. It depends on if you are talking about one conductor, one isolated conductor, then this becomes the potential. If you have a combination of conductors, then this will become potential difference. So that means your capacitance will be equal to Q divided by delta V. Delta V is gamma Q into B minus A divided by AB. AB will go up in the numerator. So your Q and Q will go, your C will come out to be, that's gamma, this is 1 by 4 pi epsilon naught, 4 pi epsilon naught will go up and you get 4 pi epsilon naught AB divided by B minus A. Now that is the capacitance of spherical capacitor, 4 pi epsilon naught AB. Now again, this equation, this result demonstrates again that thing that the capacitance of a capacitor depends on geometry, it depends on the medium. Because you can see that it depends on the radii of inner and outer spherical shell. It depends on epsilon naught, that means depends on medium. So that's one more example, that's a capacitance of a spherical capacitor. Let's talk about one more capacitor here. Although you will rarely find question on that, but let's write it down. That is the capacitance of a cylindrical capacitor. Cylindrical capacitor. Capacitance of a cylindrical capacitor. Right? I'm just going to write down the equation for this because this is not much important for us. Let's assume that I have two concentric cylinders like this. So one is this is one cylinder, and I have one more concentric cylinder here like this. These are two concentric cylinders. Let's assume that the radius of the inner cylinder is, let's say, equal to A, and the radius of the outer cylinder is B, and the length or height of the cylinder is L. Again, you repeat the same process. You give charge to the cylinder, check the potential difference, make the ratio, you get the capacitance of this cylindrical capacitor. When you do that, it will turn out to be the capacitance of this cylindrical capacitor will be equal to 2 pi epsilon naught L divided by ln of B divided by A. This is the capacitance of cylindrical capacitor. Again, you can see that it depends on geometry and it depends on medium as well. So this is all about the capacitance of a cylindrical capacitor. Now the most important thing, that is capacitance of parallel plate capacitor. Parallel plate capacitor. Let me tell you guys that now this is the type of capacitor wherein you will find in capacitors about 95 or more than 95% problems are based on parallel plate capacitor. What exactly it is? Have a look here. Let's assume that we have two plates like this and like this. Suppose that the area of each plate is A. It's A here, it's A here. Let's assume that the distance between the two plates is equal to D. Right? The medium between the two plates is, let's say, vacuum, or you can say free space, or air, because the behavior of vacuum and air is almost same, right? So you have two plates, area is A, right? Area of the plates is A, distance between the two plates is D, and the medium between the two plates is vacuum. Suppose that I give charge plus Q to this. So this charge will be uniformly distributed on the inner surface of this plate, right? And because of induction, there will be minus Q charge on the inner surface of this plate. This will be minus sign here, minus charge, negative charge on this. Here the question is that how do I give charge to this, right? That's a different topic actually, right? That's a different topic. Right now, let's assume that the charge on the inner surface of this plate is plus Q and the charge on the inner surface of this plate is minus Q. Now, before that, I write the capacitance of this parallel plate capacitor. Let's try to analyze what will be the field due to this capacitor, right? What will be the field because of this plus Q on this inner surface and minus Q on this inner surface? Let's try to analyze what will be the field because of these two plates. Right? Have a look here. The charge on the inner surface is plus Q and the charge on inner surface is minus Q. That means the charge density on this surface will be equal to Q by A, and the charge density on this inner surface sigma will be equal to again Q divided by A. I'm only writing the magnitude, that's why I omitted the sign here. So that means this inner surface carries a charge density of sigma and this also carries a charge density of sigma. In electrostatics, you have read that if you have a long plate, I assume that the plates of these capacitors are sufficiently long that I will take them as infinite. So in electrostatics, you have already read that if you have a surface, an infinitely long surface, whose charge density is sigma, the electric field due to that surface is sigma by 2 epsilon naught. It's outwards, it's away from the plate, it's away from the surface if it's positive, and towards the surface if it's negative. Which means that if I take any point inside these two parallel plates, there'll be two fields actually. One because of this positive surface, and one because of this negative surface or negative plate. The field because of this will be in this direction because it's positive, and that will be equal to sigma by 2 epsilon naught, while sigma is the charge density. And the field at the same point because of this will be again sigma by 2 epsilon naught, and that will be also in the same direction because that's a negative charge. which means that the net field inside, I call this as E naught. The net field inside will be equal to sigma by 2 epsilon plus sigma by 2 epsilon. That will be equal to sigma by epsilon naught, or I can write it as Q by A epsilon naught. This is the electric field inside the plates of the capacitor, or electric field inside the capacitor. And fact of the matter is that since I have considered them to be infinitely long, so that means this field at every point will be same, because when you have an infinitely long surface, the field at every point is constant, and that is sigma by 2 epsilon naught. So that means the field inside the plates of the capacitor everywhere is same. That means the field inside the capacitor is uniform, and the value is sigma by epsilon naught, or Q divided by A epsilon naught. Now coming back to my actual task. I want to know what's the capacitance of this parallel plate capacitor, right? For that, I have to give charge. I have to check the potential difference, right? So I have already given charge Q. Now the job to be done is check the potential difference. From electrostatics, you know that the potential difference between these two plates, potential difference between the plates, the potential difference between the plates, that's V. I call this as, let's say, delta V, or simply V. That will be equal to, I'm sure that you must have heard about this equation in electrostatics. That's equal to field into distance between the two plates. That's E into D. So now I know the value of E, or E naught, right? So I get the potential difference delta V. That's equal to Q by A epsilon naught into your D. That's a potential difference between the plates of the capacitor, QD by A epsilon naught. I have the charge, that's Q. I check the potential difference, that's QD by A epsilon naught. I can easily find the capacitance of this parallel plate capacitor. So the capacitance of this parallel plate capacitor, that is C is equal to Q divided by delta V. So your C is equal to, charge given is Q, delta V is QD by A epsilon naught. A epsilon naught will go up in the numerator, so you get Q and Q will cancel out. Your C is equal to A epsilon naught divided by D. So let me tell you guys that this equation is going to be very, very important for us. Capacitance of a parallel plate capacitor, C is equal to A epsilon naught by D. Again, it depends on the geometry, it depends on area of the plates, it depends on the distance between the two plates, and it also depends on the medium. That's why it depends, it depends on epsilon naught. So that is your, what we call as parallel plate capacitor, the capacitance of a parallel plate capacitor, right? So as I already told you in the introduction, that whenever you give charge to the capacitor, it stores charge, and by storing charge, it actually stores the energy. Now let's know and let's calculate, when a capacitor stores charge, how much energy it stores. For that, we take the examples of this parallel plate capacitor, that is energy stored by capacitor. Energy stored by capacitor. That is our next topic. Energy stored by capacitor. Right? Now have a look here. As I already told you a while ago that I am giving charge to the parallel plate capacitor. How do we give that? Have a look here. Let's assume that you have a parallel plate capacitor here. You have a parallel plate capacitor here. You want to give it, let's say, charge Q, plus Q here and minus Q here, right? The area of the plates is A. The distance between the two plates is, let's say, D. The charge you want to give to this parallel plate capacitor, that's plus Q, or Q, simply, capital Q, right? How do I give it? So what we do here is that, we connect this parallel plate capacitor to a battery. This is a parallel plate capacitor here. We connect it to a battery. Let's assume that the potential of the battery is V. So what this battery will does is that, since this positive plate is connected to positive terminal of the battery is connected to this plate, and negative terminal of the battery is connected to this plate. So, crude way, if I tell you that, this battery sucks the charge from this plate and gives it to this plate. which means that it sucks the positive charge from this plate and gives it to this plate. And the process goes on till the capacitor is fully charged. It gets a charge of plus Q. In some intrinsic state, as the charge builds on the capacitor, let's assume that the charge that has been built on the capacitor, it is plus Q here and minus Q here. The battery is getting the charge. It's building up the charge on the capacitor, right? Already it has built up the charge of Q on both the plates, plus Q on here and minus Q here, right? Now, once this amount of charge builds up, in the capacitor, electric field is developed between the plates of the capacitor like this, in this direction, from positive plate to negative plate. Potential difference gets developed, and that's obviously equal to the potential of the battery, that's equal to V, right? Now, suppose that this battery wants to move further dq charge from this negative plate to positive plate. Understand this thing. The battery is building up the charge of the capacitor. It has already built up a small q charge in the capacitor. Now it wants to build further, it wants to take dq charge further from negative plate to positive plate. So that means actually the charge is taken from the negative plate to the positive plate. That means against the field, against the potential difference, because the positive plate is at higher potential and the negative plate is at lower potential. So the battery is trying to take dq amount of charge from lower potential to higher potential. And that will not happen on its own. For that, the battery has to do some amount of work to take dq charge from negative plate to positive plate, from lower potential to higher potential, right? Otherwise, because the charge has a tendency to go from higher to lower, but the battery is taking from lower to higher. So for that, the battery has to do the work. Right? How much work is to be done the battery in taking further charge dq from negative plate to positive plate? That small amount of work done that the battery needs to do will be equal to the charge that needs to be transferred, that's dq, into potential difference. Guys, this is the equation which comes from your electrostatics, that when you put charge q in a potential difference V, the potential difference V does a work of Q into potential difference. Since the Q here is dq, so work done by the battery will be equal to dq into V. Right? Now coming back to the capacitor. Since when already Q amount of charge has already built up on the capacitor, electric field has developed from the positive plate to the negative plate, potential difference has developed. So this E here will be obviously equal to, if I write it here, this E here will be equal to charges Q divided by A epsilon naught. That's the amount of electric field that will be developed inside the plates of the capacitor, between the plates of the capacitor. Right? So I can write it like this. So dW is equal to dQ into how much charge has built up on the capacitor. That's Q. What is the capacitance? Let's assume that the capacitance is C. So what will be the potential difference? This potential difference V will be equal to Q divided by C. So I will write V as Q divided by C. This is the amount of work that the battery needs to do to take dQ amount of charge from negative plate to positive plate. Right? That's a small work done. Moving forward. So the small work done, dW, is equal to Q by C into dQ. That's a small amount of work done that the battery needs to do to take dQ amount of charge from negative plate to positive plate. But what is the maximum amount of charge that this battery is going to build up on the plates of the capacitor? That's capital Q. So the job is to find the total work done the battery needs to do to build up capital Q amount of charge on the capacitor, right? So for that, I need to integrate it. So for total work done, I will integrate it. I get W is equal to integration Q by C into dQ. Since your capacitance is constant, it will come out. So I get here W is equal to 1 by C into integration of Q into dQ. right? What was the initial charge in the capacitor? That was 0. What's going to be the final charge in the capacitor? That's Q. So what will be the total work done in building up charge capital Q is given by this. So this is Q0 and this is Q. So what I get here is something like this. So my W, that's total work done by the battery in building up capital Q charge, will be equal to 1 by C. Integration of Q dQ is Q squared divided by 2, and the limits will go from 0 to capital Q. So if you put on the limits here, so you get W is equal to Q squared divided by 2C. That is the work done by the battery in building up capital Q on the capacitor, on the plates of the capacitor. Now this work done by the battery, is actually stored inside the capacitor, right? And that's what we call as energy stored by the capacitor. So energy stored by the capacitor, energy stored by capacitor, energy stored by capacitor. Let me call this as U, that U will be exactly equal to the W. That's what I told you. The work done by the battery in building up charge capital Q on the capacitor, this work done is stored inside the capacitor in the form of energy, in the form of electrostatic potential energy, right? So electrostatic potential energy, or simply I will call as energy stored by the capacitor, that's U, will be equal to Q squared divided by 2C, and this is the first formula for energy stored by a capacitor, Q squared by 2C. Right? Since I took the example of a parallel plate capacitor, but this equation is valid for every other capacitor, be that spherical capacitor, be that cylindrical capacitor, or any other capacitor. Energy stored is equal to Q squared by 2C. Now, since we have a formula here that your Q is equal to CV. So when I put the value of Q here as CV, I get one more equation. So I get U is equal to Q as CV. I get 1 by 2 CV squared. That becomes one more equation for what we call as energy stored by the capacitor. Right? Or one more, I can write C is equal to Q by V. From here, C is equal to Q by V. I put the value of C as Q by V. I get one more equation, U as Q squared by 2C. So I get 1 by 2 QV. That's one more formula for energy stored by the capacitor. Q squared by 2C, 1 by 2 CV squared, 1 by 2 QV. So all these equations give me the energy stored by the capacitor, right? So that's all about your energy stored by the capacitor. Moving ahead here. Now you see, let me go back to the parallel plate capacitor here. You have a parallel plate capacitor like this. This is one plate, this another plate, it is positive plate. Let's assume that the charge on this positive plate is plus Q and the charge on this negative plate is minus Q. Area of each plate is A. Distance between the two plates, let's say D. So it's a logical thing that since the charge on this plate is plus Q and the charge on this plate is negative Q, they will be attracting each other. So our job is to find what will be the force between the plates of the capacitor, right? I want to know what is the force between the plates of the capacitor. Force between the plates of the capacitor. Force between the plates of capacitor. Now check here. Now you see, what's the charge on this plate? It's plus Q. What's the area of this plate? That's A. What will be the charge density on this plate? Sigma. That will be equal to Q divided by A. Right? So since the charge is on this, positive charge is here. Right? The charge density is sigma, that's Q by A. So you have a long surface, infinitely long surface, sufficiently long surface. The charge density is sigma. It will create electric field. I'm not talking about the total electric field inside the capacitor. I am talking about the only electric field that's created by this positive plate. Charge density sigma. The field it's going to create here, right? The field it's going to create here, that is sigma by 2 epsilon naught. Not sigma by epsilon naught. Because sigma by epsilon naught is the total field between the plates of the capacitor. So in that total field, there's a contribution of this positive plate and the contribution of negative plate, right? But I am talking about what is the field created by this positive plate, which will be actually experienced by this negative plate. So that means this negative plate will experience a field of sigma by 2 epsilon naught because of this positive plate, right? So the field experienced by this negative charge, negative plate is sigma by 2 epsilon naught, right? Since this is negative charge, so it will get attracted toward this positive plate. And what will be the force of attraction? You all know that force of attraction is equal to charge. Charge on this plate is Q into field. Field is equal to sigma by 2 epsilon naught. Right? So I have not taken the total field. Total field inside the plates of the capacitor is sigma by epsilon naught. But there's a contribution of negative charge as well, negative plate as well. Negative plate will only experience the field of positive plate, not the net field, mind it. So it will only experience sigma by 2 epsilon naught. So the force acting on the negative plate, which will be actually attractive in nature, that's a very logical thing, that will be Q into sigma by 2 epsilon naught. Since sigma is Q by A, so the force of attraction between the plates of the capacitor will be equal to Q into sigma, that's Q by A, it will become Q square divided by twice A epsilon naught. This is the force between the plates of the capacitor. Force between the plates of the capacitor, right? So the two plates of the capacitor, the two plates of the parallel plate capacitor are going to attract each other, and this is going to be the force of attraction between the two plates of the parallel plate capacitor. Moving ahead here, let's talk about one more thing. Have a look here. We already in fact derived the energy stored by the capacitor. Let's assume that the capacitance of this capacitor is C. The potential difference across the plates is V. Area of the plate is A. Charge on this plate is plus Q. Charge on this plate is minus Q. Right? The energy stored by this capacitor, I have multiple formulas. I have actually 3 formulas here, but I will use U is equal to 1 by 2 CV square. 1 by 2 CV square. Right? That's the energy stored by the capacitor. Let me talk about one more thing here. Electric field between the plates of the capacitor, which is going to be uniform field. I can show it by parallel and equidistant lines. That's electric field here. And that electric field is going to be E is equal to sigma by epsilon naught, or I can write it as Q divided by A epsilon naught. That's electric field here. Potential difference is V. Capacitance is C. Charge on the plates is Q. Area of the plate is A. Right? Now see here. Since capacitance is equal to C, so since we are talking about the parallel plate capacitor, C will be equal to A epsilon naught divided by D. Right? Because we are talking about the parallel plate capacitor here. Potential, that's V. This V will be equal to E into D. As I already told you that this equation comes from the electrostatics. Right? So if I put the values here, what I get is like this. So U is equal to, total energy stored is equal to 1 by 2 C. That's A epsilon naught by D. A epsilon naught by D into V. What's V? That's ED. And there's a square. It will become E square into G square. Alright? So 1D will cancel out. So what I am going to get here is something like this. So U is equal to, the total energy stored is equal to 1 by 2 A epsilon naught, right, into E square into G. And I'm sure that you understand the meaning of every parameter here. Right? Now see, U is equal to, I will write it like this, 1 by 2 epsilon naught E square into, I will write this A and D separately here. What's A? A is the area of the plate. What is D? You see D? D is the distance between the two plates. It's D here. So what's A into D? So this A into D is the volume of the parallel plate capacitor. A into D is the volume of the parallel plate capacitor. So this A into D is the volume of the parallel plate capacitor. So you get U. I will take this A into D here. That's A into D. That's equal to 1 by 2 epsilon naught into E square. Right? Now understand this equation. U is the total energy stored by the capacitor. A into D, that's a volume. That's a volume of the capacitor. That's a volume of the capacitor, right? That's equal to 1 by 2 epsilon naught E square. So total energy stored by the capacitor divided by volume, this is what we call as energy density of the parallel plate capacitor. Yani ki total energy stored per unit volume, right? So I call this as energy density of the capacitor, energy density, and let me represent it by small u. So my small u, which is energy density, is equal to 1 by 2 epsilon naught into E square. So you will get one more equation here. Maybe we may need it in some numericals here. So energy density of the parallel plate capacitor is equal to 1 by 2 epsilon naught E square. That's the energy density of parallel plate capacitor, right? So that's all about your first part. Right? Now, before that we move forward in capacitors, let's have a look at few examples, few problems here, right? So problems after every concept is very, very important, because problem is something why the actually your concept culminates, right? Let's have a look at few problems here. All right. Now, when we solve these problems, actually, right, it gives us more insight into the concepts, actually, right? They are very important to understand the concept fully. Let's have a look at first problem here. Have a look here. A capacitor of capacitance C, initially uncharged, is connected with a battery of potential V. Find, right? A capacitor of capacitance C, initially uncharged, is connected with a battery of potential V. Find the, number 1, final charge of capacitor. Number 2, find the amount of charge that transfers through the battery. Number 3, work done by the battery. And number 4, heat dissipated in the process. Right? Once we solve this problem, you will understand many other things, actually. Let's begin the problem. If you want to take a screenshot of this question, you can take here. All right. Let's move forward here. I am sure that you have understood the question. We have a capacitor here. Whose capacitance is, let's say, C. It's initially uncharged. That means there is no charge on the capacitor. When there is no charge on the capacitor, there will be no potential difference across the plates. So this is uncharged. Right? So initial potential on this, V initial, that's equal to 0. The charge on this capacitor, Q initial, that's equal to 0 again. Because your capacitor is uncharged, right? Now what you are doing is that you are connecting this capacitor with a battery of potential V. Now, when you are connecting this capacitor with a battery of potential V, like this, you have a capacitor here, right, whose capacitance is C. You are connecting this with a battery whose potential is V. Logical thing is that since there is no other element in the circuit, so all of this potential V of the battery will directly go to the capacitor. So that means now we have a capacitor whose potential difference is V. That means this capacitor will be charged by the battery, right? Let's have a look at this. Have a look here. I will remove the battery here. I will assume that we have connected it to a battery. We have connected to a battery whose potential is V. So that means the potential difference across the plates of the capacitor will be again V. Capacitance is C. Capacitance will not change, right? And let's now see that what will be the charge on the capacitor, because now the capacitor is charged. Right? So what will be the charge? So first thing, the final potential here, V final, now it is charged. Let me write it here. It is charged now. The final potential is obviously equal to V. The final charge Q final will be equal to, that is C into V. Capacitance is C, final potential is V. So final charge is CV. Right? What was the initial charge in the capacitor? That is 0. That is 0. What's the final charge in the capacitor? CV. Who has given this much of charge? That's a battery. Right? My first question was find final charge in the capacitor. So the final charge in the capacitor is CV. Initially it was 0, final it is CV. Second part, find the amount of charge that transfers through the battery. Now see, what was the initial charge in the capacitor? That was 0. Final charge, that is CV. So that means how much? Who has given this charge? Battery. So how much charge has come from the battery? So I call this as, that's part 2, right? The amount of charge that flows to the battery, that's I call delta Q. Delta Q will be obviously equal to Q final minus Q initial, right? Because initially it was 0, finally it is CV. So the amount of charge that has come from the battery is Q final minus Q initial. That will be delta Q will be equal to CV. That is the amount of charge that has come from the battery out. That's the amount of charge that flows through the battery. Right? That's your part number 2. Part number 3. What is the work done by the battery? That's part number 3. What's the work done by the battery? Now you see, what is the amount of charge that flows through the battery? That is CV, that's delta Q, that is CV. What's the potential of the battery? That's V, right? You see, the potential of the battery was V. Potential battery was V because that is the V which is given to the capacitor. So if the amount of charge that flows through the battery is delta Q and the potential of the battery is V, then the work done by the battery, I call this as W battery. The work done by the battery is equal to the amount of charge that flows through the battery into potential difference of the battery, that's V. Right? Let me make it a little more clear here. You see that in electrostatics, if you have a potential difference V between these two plates or between these two terminals, and you put a charge Q here, the charge Q flows through this potential difference. The charge Q is in potential difference V. The work done by the potential difference is equal to Q into V. This is a very common equation in your electrostatics, right? Coming back here. So the work done by the battery is amount of charge that flows through the battery into potential difference of the battery, that's V. So work done by the battery is equal to delta Q is CV into V. The work done by the battery is CV square. Work done by the battery is equal to CV square. Right, that's my part 3. Work done by the battery. Then D. What's the heat dissipated in the process? Let's first try to understand where from this heat comes. You see that if I again make it for you here, this was a capacitor, it was connected to a battery. It was connected to a battery of potential V here, right? Now this battery is a source of energy for this circuit. This battery is the source of energy for this circuit, right? And how much energy it supplies to the circuit, that's exactly same as that of the work done by the battery. It is same as that of the work done by the battery. That's the amount of energy which this battery supplies to the circuit. So that is, in our case, the amount of energy that is supplied by the battery to the circuit, that is CV square. Now what happens to the CV square? Remember always, the amount of energy supplied by the battery to this circuit, a part of the energy is utilized to give energy to this capacitor, and a part of the energy supplied by the battery is dissipated in the form of heat. So that means, again I'm repeating, that this battery is a source of energy to the circuit. That energy given by the battery is utilized for two things. One, to give energy to the capacitor. Two, a part of the energy supplied by the battery is dissipated in the form of heat. So which means that what is the total energy or what is the total work done by the battery? That is CV square. This work done by the battery, W battery, will be usually utilized for two things. One, to change the energy stored by the capacitor, plus the left part of the energy is dissipated as heat. Remember, this is simply a conservation of energy. The total energy supplied by the battery, that's a work done by the battery, is utilized for two things. One, to change the energy stored by the capacitor. Two, and a part of the energy goes into heat. Which means that heat dissipated will be equal to work done by the battery minus delta U. Right? If you go back here, what was the initial potential of the capacitor? That was zero. Initial charge of the capacitor, that was zero. Then what will be the initial energy stored by the capacitor? That will be obviously equal to zero. Now, what is the capacitance of this capacitor? C. What is the potential of this capacitor? Now, that's V. Then what will be the final energy stored by this capacitor? That will be obviously 1 by 2 CV squared. 1 by 2 CV squared. Now, that takes me into this thing. Heat dissipated in the process equal to work done by the battery. I'm sure that you're writing each and everything here. Work done by the battery will be obviously equal to CV squared minus delta U. That's U final minus U initial. Since U initial was 0, so I will write it here only. U initial was 0. All what we have U final, and U final is 1 by 2 CV squared minus 0. So heat dissipated in the process is CV squared minus half of CV squared. So heat dissipated in the process is CV squared by 2. That is the amount of heat dissipated in this circuit. So let me go back, have a look at what we were supposed to do and what we did. We were supposed to find the final charge in the capacitor. We did that. That is CV. We were supposed to find what will be the amount of charge transferred for the battery. That is Q final minus Q initial. That is CV. We were supposed to find what's the work done by the battery, and that's equal to the amount of charge that flows from the battery into potential. We got work done by the battery, and then we are supposed to find heat dissipated. I'm again telling you that the battery is the sole supplier of energy in the circuit, and that energy is utilized for two things. One, to change the energy stored of the capacitor, and a part of the energy is dissipated as heat, right? So heat dissipated here comes out to be CV squared by 2, right? One important thing I will tell you, one interesting thing actually I will tell you here. What is the work done by the battery? Or. What's the energy supplied by the battery? CV square. Right. What is the heat dissipated in the circuit? CV square by 2. What exactly that means? Half of the energy supplied by the battery is dissipated as heat. And let me tell you guys that it always happens. Irrespective of what kind of question you talk about, this will always happen. That if the energy supplied by the battery is X, the amount of heat dissipated will be always equal X by 2. I hope that you will remember it for many other questions to come. Let's move to next question. Let's have a look at this question, which again same actually. It's again same, right? Question tells me a capacitor of capacitor C is initially charged up to potential V. In the previous question, the capacitor was initially uncharged. It is charged to a potential V. That means you have got the initial potential difference. You'll be having the initial charge. Is then connected to a battery with potential difference V by 2. Now you are disconnecting it from first battery and connect it to another battery whose potential difference is V by 2. After a long time, find number 1, total charge flow to the battery, work done by the battery, heat dissipated. Right? Have a look here. See, we have a capacitor here. Let me say that the capacitor is C. Potential difference across the plates of the capacitor is V, which means that initial charge on the capacitor will be CV, which means that initial energy stored by the capacitor will be equal to 1 by 2 CV square. Initial potential difference is V, initial capacitance is C. Now what you did is that you connected this capacitor with a battery of potential difference V. You did it like this. You have a capacitor now. Right? You connected it to a battery of potential difference V. Right? Now the same potential difference V by 2 will go to the capacitor. Now the potential difference across the plates of the capacitor will be no more V, but it will be V by 2, because potential difference across the plates of the capacitor is decided by the battery. So that means if I cut it here, I have another capacitor here like this. Right? Capacitance will not change, that will be C. Potential difference will not be V, it will be V by 2, which means that final charge will be C into V, but that will be C into V by 2. Right? Final energy stored, U final, will be equal to 1 by 2 CV square, CV square, that will be V square by 4. That means final energy stored will be equal to 1 by 8 CV square. 1 by 8 CV square, right? So I wrote every data here. Now, the first question which I'm asking, find the amount of charge that flows through the battery, right? Find the amount of charge that flows through the battery. Check here. What was the initial charge on the capacitor? That was CV. What is the final charge on the capacitor? That is CV by 2. In the previous case, the initial charge was 0, final charge was CV. So the charge has come from the battery. How much? CV. Now, what is the initial charge on the capacitor? CV. Final CV by 2. That means charge on the capacitor has decreased. How much? Half. Initially it was CV. Now CV by 2. So in the first case, the charge has flown from, in the first case, the previous question, from battery to the capacitor. In this case, the charge has gone from the capacitor to the battery. So if I go for the first part, what is the amount of charge that flows to the battery? That's delta Q. That will be obviously equal to Q final minus Q initial, right? So your delta Q, the amount of charge that flows through the battery, delta Q will be Q final, CV by 2 minus CV. That will be obviously minus CV by 2. The minus sign here tells you that the charge has not flown from battery to capacitor, but from capacitor to the battery. So that's the amount of charge that flows through the battery. Number 1. Number 2, what I'm asking, that is work done by the battery. As I already told you that the work done by the battery, W battery is equal to potential difference of the battery, that's V, into amount of charge that flows, that's delta Q. That means work done by the battery is equal to minus CV by 2 into V. That will be minus CV squared divided by 2. That is the work done by the battery. And then I go to the third part, what is the heat dissipated? As I already told you that the work, don't go to the minus side. The work done by the battery is CV squared by 2. Let's not talk about the negative sign. Then tell me what will be the heat dissipated in the process. It will be half of that. That means CV squared by 4. As I already told you this concept in the previous problem. Because heat dissipated is always equal to half of the work done by the battery, right? So in this case, that's third. Heat dissipated is equal to work done by the battery. That's this. That will be equal to CV square divided by 4. If I put a negative sign here as well, let it be. Or if you want to calculate it, how much will be the heat dissipated? Check it. I told you that work done by battery is equal to change in energy stored by the capacitor plus H. That means your H is equal to work done by battery minus CV square by 2 minus delta U. Delta U is, actually you get work done by battery minus delta U. So minus delta U. U final. What's U final? That's 1 by 8 CV square. It's 1 by 8 CV square. Minus U initial. What's U initial? It's a 1 by 2 CV square. Right? You solve it, and once you solve it, what you are going to get is something like this. H is equal to, oh, I did a blunder here. It is work done by the battery is potential of the battery into charge flow. Potential of the battery is not V, it's V by 2 now. So that means the work done by the battery will be delta Q CV by 2 into V by 2. It will be CV square by 4. Okay? So accordingly, it will be heat dissipated will be CV squared divided by 8. Because potential of the battery is not V by 2. Moving ahead here. right? So it is minus CV square by 2, minus CV square by 2, right? Okay, minus CV square by 8, okay, minus plus CV square by 2, right? This and this will go. Heat dissipated is equal to minus CV square divided by 8, and that's what I told you earlier here. It is minus CV square by 8, right? Remember it once for all. Heat dissipated in the process is always equal. In these questions, work done by the battery divided by 2. Half of the energy supplied by the battery is dissipated in the form of heat. All right, so that's all about this question. Moving to next question. Now have a look here. A capacitor of capacitance 5 microfarad is charged to 5 microcoulomb, right? If the plates are pulled apart to reduce the capacitance to 2 microfarad, how much work is done? Have a look here what this question is all about. You have a capacitor here. There is some distance between the plates of the capacitor. Question tells me the charge on this capacitor is 5 microcoulomb. Capacitance Q initial, let me say. Initial capacitance C initial, that's equal to, I think, 5 microfarad. Yes, that's 5 microfarad. 5 microfarad, right? Now what you are doing is that you're pulling the plates apart. You're pulling the plates apart. You're increasing the distance between the two plates. Now, when you're increasing the distance between the two plates, capacitance of the parallel plate capacitor will decrease, because capacitance of the parallel plate capacitor is inversely proportional to D. Now, question tells me you have pulled the plates of the capacitor apart, right? Capacitance now, yani ki final capacitance becomes, I think, 2 microfarad. Yes, it becomes 2 microfarad. It becomes 2 microfarad. My question is that what will happen to the charge? And let me tell you that the final charge will be same as that of the initial charge, 5 microcoulomb. Reason? Because this capacitor is an isolated system. It doesn't matter whether you move them apart, plates, or you bring them closer, charge is not going anywhere because it is not connected to any other system where the charge is going to flow. It's an isolated system. The charge on the capacitor is going to remain constant. So it will be again 5 microcoulomb. So you have initial capacitance, initial charge, final capacitance, final charge. You're asked what will be the work done? What will be the work done? So first point you need to understand is that the work done is required. The work done for sure is required because you are pulling them apart. There's attractive force between the plates and the capacitor, so you need to exert force. You need to do the work. So how much work is done? What I will do is that I will find the initial energy stored, U initial. That will be equal to Q initial square, because I have a formula, Q square by 2C energy stored, Q initial square divided by twice C initial. I will calculate the initial energy stored. I will calculate the final energy stored, U final, Q final square divided by twice C final. I will calculate the final energy stored, right? I will calculate both the things. When I do that, again, I have to take help of something which comes from your, what we call as work power energy from the alarm portion. That work done by external force is equal to change in potential energy, and here it will be the work done in pulling the two plates apart will be equal to change in electrostatic potential energy stored by the capacitor. So that means here W will be equal to U final minus U initial. So if I calculate it here, so W will be equal to what's U final? It is Q final square by twice C final minus Q initial square divided by twice C initial, right? Since Q initial, Q final is same, I can get it out. W is equal, I can get it out. Right, when I get it out, what I get is 1 divided by twice. What is C final? Q initial and Q final is same, that's 5 micro. Micro means 10 power minus 6 into twice C final. C final is twice 2 microfarad. 2 into 10 power minus 6 minus 1 divided by twice. In fact, you can get 2 out as well. Yes, you can get 2 out as well. You can get 2 out as well. It's divided by 2. So it is, let me write it again. It will be 2 microfarad, that's 2 into 10 power minus 6. All right. The minus initial was 5 microfarad, 5 into 10 power minus 6. All right. Right. In fact, you can get 10 power minus 6 out as well. 10 power minus 6, 10 power minus 6 will go. So you get W is equal to 5 by 2 into 1 by 2 minus 1 by 5. It will be 5 minus 2 divided by 10. Right. So work done by the external agency will be equal to 5 by 2 into 5 minus 2 divided by 10. That will be 3 divided by 10. 5 ones, 5 twos. So W external will be equal to 3 divided by 4. That's your answer. In fact, there's a square. I did it wrong. I did it absolutely wrong. I did it absolutely wrong because there's a square as well. There's a square as well. So W is equal. I'm sure that you will do it yourself. Now it's only about, putting the values here. So you get the work done by the external agency. So the point here is that the work done by the external agency will be given by the change in electrostatic energy stored. Change in electrostatic energy stored. All right. So that was all about this question as well. Moving to next question. Now have a look here. Question tells me one plate of parallel plate capacitor is fixed, other end is connected with a spring. Capacitor is uncharged. The separation between the plates is D. And spring is in natural state. Natural state means there's no compression or there's no elongation in the spring, right? When capacitor is connected across battery, the separation between the plates is 0.8 D. Area of the plates is A. Find the force constant K of the spring. If you want to take a screenshot before we solve it, discuss it, take a screenshot here. All right. Now I have made a diagram here, right? Let me make it a little more simple for you. I have a capacitor here. This capacitor is connected with a spring. This capacitor is connected with a spring whose spring constant is K. Distance between the plates is D. Area of the plates is A. All right. Now what you did is that you connected a battery to this capacitor like this. Have a look. Like this. You connected a battery whose potential is V. Like this. Whose potential is V. So this whole V will go to the parallel plate capacitor. There'll be a charge, positive charge here. There'll be a negative charge here. Right? There'll be a negative charge here. So because of the charge will be developed on the plates, the capacitor will be charged. There will be a attraction between the two plates. So when there's attraction between the two plates, right, this spring gets elongated. This spring will get elongated. It will be, pulled by this negative plate towards itself. Right? Question tells me now the distance between the two plates is no more D. It was initially D. Now the distance between the two plates is 0.8 D. That means how much this plate has come towards the positive plate. It is 0.2 D. That means the amount of stretch, amount of elongation in the spring will be 0.2 D. Initially it was D. Now it is 0.8 D. That means the elongation that has happened in the spring is 0.2 D. So when there's an elongation in the spring, so a spring force will be developed here, and that spring force will be equal, let's say, Kx, where x is equal to 0.2 T. Kx. This will stop here. This will stop only there when the electrostatic force between them is equal to the spring force. This plate will come in equilibrium. There'll be no elongation. There'll be no sliding of this plate, right? Let's see now what is the force of attraction between these two. What is the force of attraction between these two? And that force of attraction will be exactly equal to Kx, right? So what's the force of attraction? We have written that force of attraction between the plates will be equal to K into X. Right? What's the force of attraction? If you remember that correctly, force of attraction is Q squared divided by twice A epsilon naught if you remember it, epsilon naught D, I think. It was, yes, absolutely. Force between the plates of capacitor, it was Q squared divided by twice A epsilon naught. Yes, it was Q squared by twice A epsilon naught. And that has to be equal to K into X. Right? I had to find K. But you have to first understand, now it's only about, playing with the equation. It's only about playing with the equation. First, you have to understand that the distance between the plates was D. Spring was in its natural state. Relaxer, no elongation, no compression. You connect a battery. When you connect a battery, this will be charged. When this is charged, there will be a force of attraction between the plates. So force of attraction is between the plates. So this plate will pull the spring. This is elongation 0.2 D, and the distance between the two plates is left with 0.8 D. Right? So now I am supposed to find K. So I went with the equation that F will be electrostatic force of attraction between the two plates, that's F will be equal to Kx. So Q squared by twice A epsilon naught is equal to Kx. Alright. So now the point is Q is not given. I know that Q is equal to CV square. So I get C square V square because Q is equal to CV divided by twice A epsilon naught. That's equal to Kx. That's equal to Kx. So I continue with this equation. C square V square divided by twice A epsilon naught is equal to K into X. I will write C as A epsilon by D, but not D here, it is 0.8 D now, right? So C is equal to A epsilon naught divided by 0.8 D. Right? You put the value of C here, so what you get is C squared, that's A square, epsilon naught square, V square divided by, twice A epsilon naught D square, right? And 0.8 square. I hope you got it what I did here. That's a simple calculation. And that's equal to K into X. So, and I can put the value of X as well. That's equal to 0.2 D, right? I can put X as well. Now you modify this equation, you get the value of K, and the K you will get A square epsilon naught square. In fact, one epsilon will go here. You will write only epsilon naught into V square potential square divided by, twice. In fact, A will also go here. So you'll be left with only one A here, right? It will be twice. It is D square into D, that will be D cube, right? Then that is 0.8 whole square, that will be 0.16 into 0.2. You further solve it, you get the value of K here, all right? So moving forward to next topic. Let's talk about sharing of charge and common potential. Sharing of charge and common potential. Now have a look here. What kind of situation, what kind of problem we are talking about. Let's assume we have two spherical conductors. This is one spherical conductor. This is another spherical conductor. All right. Let's assume that the radius of this conductor is R1. The radius of this spherical conductor is R2. All right. The charge given to this conductor is Q1. The charge given to this conductor is Q2. Potential of this conductor, let's say that's equal to V1, and potential of this conductor is V2. Energy stored by this conductor is U1. Energy stored by this conductor is, let's say, U2. Capacitance of this conductor is C1, which will be obviously equal to 4 pi epsilon naught R1, and capacitance of this spherical conductor is C2. All right, they're isolated. They are sufficiently apart from each other. That is, they do not interact. Now, what I did here is this. I joined them by a connecting wire. Like this. Have a look here. Now, this is your conductor. And this is your conductor. And I'm joining them by a connecting wire. Like this. This is a connecting wire. Now, what will happen here? Since this sphere or a spherical conductor is at potential V1 and this spherical conductor is at potential V2, which means that there is a potential difference between the two conductors, right? So what exactly that means? That means when you connect them by a connecting wire, since there's a potential difference, charge will flow from high potential to low potential. Now it depends on which of them is higher, whether V1 is higher or V2 is higher. If V1 is higher, charge will flow from the first conductor to second, or if V2 is higher, charge will flow from second spherical conductor to the first conductor. Irrespective of which one is higher potential, since there's a potential difference, so charge will flow through this connecting wire. So for how long charge will flow? Charge will flow till the potential of both the conductors become the same. So that means they come to the common potential. And when that happens, since the charge flow takes place, if the initial charge of this conductor is Q1, now let me assume now the charge is Q1 prime. The charge on this conductor was Q2, let's assume it's Q2 prime. The potential was V1, now let's assume potential is V. Energy stored was U1, let's say it is U1 prime. Here the potential was V2, again the potential will be same here because they will reach the common potential. Energy stored was U2, now suppose it will be U2 prime. Capacitance initially was C1, that will be again C1, and here it will be again C2 because the capacitance is not going to change. So that is the situation we are talking about. You have two spherical conductors with all the parameters given. You are connecting them up by a wire. Since there's a potential difference, charge will flow through the wire. There will be a current through the wire. The parameters will change. The charge on this conductor will change. Potential will change. Energy stored will change. But the capacitance will remain same because capacitance has nothing to do with the charge and potential. That depends on the geometry and the medium. Since that is not changing, so capacitance will remain the same. In this scenario, I'm asked 3 questions or maybe 4 questions. Let's talk about it one by one. The first question I'm asked here is this: what will be the final charge on the two conductors? That means I'm supposed to find Q1 prime and Q2 prime. That's number 1. Number 2, I'm supposed to say and supposed to answer what will be the common potential, since the potential of both the conductors will be same. Let's say that's equal to V. That's number 2. And number 3 is that when there will be a charge flow through the connecting wire, when there will be a current through the connecting wire, it's a very obvious thing, heat will be dissipated. So that means there are actually 3 questions. Number 1, what will be the final charge on the two conductors? Number 2, what will be the common potential? And number 3 will be what will be the heat dissipated when there will be a flow of charge, when there will be a current through this wire. All right. But once that happens, that flow of charge happens, you must understand that the total charge will always remain conserved. But exactly that means if the initial charge here was Q1, initial charge here was Q2, the total initial charge was Q1 plus Q2, the final charge here is Q1 prime, final charge here is Q2 prime, the total final charge is Q1 prime plus Q2 prime. Initial total charge will be always equal to final total charge because charge is always conserved. That's the first principle that this situation has to follow. So that means I'm going to write here, that is this Q1 plus Q2 will be always equal to Q1 prime plus Q2 prime. And let's say that that's equal to total charge Q. I call that as Q. Now this equation is very important. That simply comes from what we call as conservation of charge. The total charge will be always conserved. Now, since I told you, I'm asked 3 questions. Final charge, common potential, and heat dissipated, right? Now, let's talk about the first one. That is, what will be the final charge? What will be the final charge on each conductor? What will be the final charge on each conductor? So I don't think that I need to derive it here. I will simply write down the equation. But let me tell you that this equation comes from the simply conservation of your charge. Since final charge is Q1 prime, your Q1 prime is equal to your total charge Q. which is Q1 plus Q2, or Q1 prime plus Q2 prime, into radius of that sphere, that's R1, divided by R1 plus R2. This will be the final charge on sphere 1, that is this sphere, your Q1 prime. Q1 prime will be equal to Q, that's total charge, into R1 divided by R1 plus R2. That's final charge on first sphere. Similarly, the final charge on the second sphere, that's Q2 prime, that will be again equal to total charge, that's Q, into radius of that particular sphere, that's R2, divided by R1 plus R2. This will be the final charge on these two spheres. I have not derived it here. I don't need to derive it here. But let me tell you that it actually comes from what we call as conservation of your charge. Because charge has to be conserved, and thereby we get these two equations. That's my first question. What will be the final charge on the two spheres? Number one. Number two question which I'm asked here, what will be the common potential? Common potential. Common potential. When you connect these two spherical conductors, the charge flow will take place till they reach the common potential. I'm supposed to find that common potential here. I'm supposed to find this V, right? That common potential. Now, since you connected both the conductors, now it's a single system. You know that the total potential is given by total charge divided by capacitance. Mind it again, what I'm saying. When you connected these two conductors by a wire, it becomes a single system. So if you have to find the potential of this system, that will be simply given by total charge divided by total capacitance, right? Have a look here. So if I have to write the common potential here, if I have to write the common potential V, that will be equal to total charge. Total charge is Q1 prime plus Q2 prime divided by total capacitance, that is C1 plus C2. Or you can write it as Q2 prime, or you can write it as Q1 prime plus Q2 prime is equal to Q1 plus Q2 as well, which was the initial total charge. You can write it as Q1 plus Q2 divided by C1 plus C2. This is one more equation. Or you may write it as Q divided by C1 plus C2, because Q is again total charge. Now, we can write one more equation. Now, have a look here. The charge on this sphere is Q1, capacitance C1, potential V1. Can I write Q1 is equal to C1 V1? Obviously, not a big deal. Here, Q2, that's equal to C2 into V2, right? Because we already know this equation. So that means that gives me one more equation here, and that's V is equal to Q1 plus Q2, C1 V1 plus C2 V2 divided by C1 plus C2. That will be the final potential or common potential on both the spheres. That's number one. And number two. Now moving to number three, that is what will be the heat dissipated. When this charge flow takes place, what will be the amount of heat dissipated? First question is that how heat will be dissipated and why heat will be dissipated? Simple answer. Simple answer. When there's a charge flow through the wire, through this connecting wire, there's a current flowing through this connecting wire. And when there's a current flowing through this wire, you got to go back to the Joule's law of heating. Obviously, there will be a heat dissipation. So what will be the amount of heat dissipation? Have a look here. Have a look here. Now look, what was the total energy stored by this conductor initially before connecting? That's U1. What was the total initial energy stored by this conductor? That's U2. What was the total initial energy covered by both? That's U1 plus U2. U1 plus U2. Now after you connect them, the energy stored by both the conductors will change. It's U1 prime and U2 prime. Then what is the final total energy stored by both the conductors? That's U1 prime plus U2 prime. Have a look here. So if I have to see what was the total initial energy stored, that will be U1 plus U2. What will be the total final energy stored? That's U final. That will be equal to U1 prime plus U2 prime. But the fact of the matter is that if you actually check it in the numerical, that U final will be always a little less than U initial. The total final energy stored, that's U1 prime plus U2 prime, will be little less than total initial energy stored, that's U1 plus U2. That means U Final will be little less than U initial. Question is, why does that energy go? That is the amount of energy which is actually dissipated in the form of heat. So that means the amount of heat dissipated here will be equal to U final minus U initial. U final minus U initial. Now, when you solve what is U initial equal to and U final equal to, you put the values here, U final minus U initial, you will see that the amount of heat dissipated in this process, that's H, is equal to 1 by 2 C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. This is the amount of heat dissipated in this process, right? You may wonder, sir, why from you got this equation? It is very simple. See, I don't want to derive it because that's not required. I need U1. U1 will be equal to 1 by 2 C1 V1 square. U2 will be 1 by 2 C2 V2 square. Total energy will be 1 by 2 C1 V1 square plus 1 by 2 C2 V2 square. And similarly, you do it here, right? Then you make U final minus U, in fact, U initial minus U final, to be more precise, U initial minus U final, because obviously U initial will be little more than U final. So it will be U initial minus U final. When you put all the values here, you get the amount of heat dissipated in the process. That's 1 by 2 C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. That's initial potential on both the conductors, right? But along with that, I can stretch these equations to one more situation actually. I can use these equations to one more situation. What is that? Have a look here. Suppose I have two capacitors, parallel plate capacitors. Until now, I was talking about the two conductors, right? I have two capacitors here. This is, let's say, positive plate. This is negative plate. Let's assume that the capacitance is C1, potential is V1, energy stored is U1. All right. Charge on the capacitor is, let's say Q1. All right. And you have one more capacitor here. This is positive plate. This is negative plate. Let's assume that capacitor is C2. Potential of the capacitor is V2. Energy stored is U2. And the charge on the capacitor is Q2. Right? Now you are connecting these two parallel plate capacitors. In the previous situation, you were connecting the two spherical conductors. Now you are connecting the two parallel plate capacitors in such a way that you are connecting positive plate with positive plate and negative plate with negative plate. When I do that, positive with positive, negative with negative, again I'm asked these three questions. What will be the final charge on the capacitors? Number one. Number two, what will be the common potential? And number three, what will be the amount of heat dissipated? Again, I'm going to write down the equations for that, and they will be symmetrical with the previous situation. Number one, what will be the final charge after connecting? What will be the final charge after connecting? Let me write it here. After connecting. Right, what will be the final charge? In the previous case, the final charge Q1 prime was total charge into radius of that sphere divided by sum of the two radii. In this case, the final charge Q1 prime will be equal to total charge Q into capacitance of that capacitor C1 divided by sum of the two capacitances C1 plus C2. And accordingly, after connecting, the charge on this capacitor, that's Q2 prime will be equal to total charge, that's Q, into capacitance of that capacitor, that is C2, divided by sum of the two capacitances C1 plus C2. Now you see that the equations here and in the previous case, the equations are symmetrical. The only difference here is that it was in the previous case Q total charge into R1 divided by R1 plus R2. Q2 prime, Q total charge, R2 divided by R1 plus R2. Now the only difference is its capacitance here, right? That's first question. Final charge. Number one. Number two, what will be the common potential? Exactly same equation. What will be the common potential? Your common potential will be equal to, again, total charge So that will be equal to Q1 plus Q2 divided by total capacitance, that is C1 plus C2. Or you may write it as common potential C1 V1 plus C2 V2 divided by C1 plus C2. This will be the common potential. Number 2. And number 3, again one more thing, that's what will be the heat dissipated. What will be the heat dissipated? Like in the previous case, like we discussed, that when you connect the two capacitors, the total final energy will be a little less than the total initial energy. So that part, the amount of energy which is less, that is the amount of energy which will be dissipated in the form of heat. So that is, again, I am going to write here, the amount of heat dissipated here will be equal to U initial minus U final, because U initial will be greater than U final will be little less than U initial. Again, when you put all the, values here, the heat dissipated here turns out to be 1 by 2 C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. This is the amount of heat dissipated in the process. All right. Now, so that is what I have to talk about when it comes to the equation. So I'm sure that here I took a liberty of not, deriving the equation, but theoretically I told you that where from these equations actually come. Right? But now let me go a little in detail about these two equations. That is common potential and heat dissipated, because you'll find a good number of problems on these two asked in your competitive examinations. Right? Let's take these two equations actually. Let me write them actually again. Your common potential, that's V. That's equal to C1 V1 plus C2 V2 divided by C1 plus C2. All right, number 1. And number 2, what's the amount of heat dissipated at? That's equal to 1 by 2 C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. All right, so these two equations are very important. You'll find a good number of problems asked on these two equations. All right, now suppose case number 1, and I'm sure that you are going to remember these cases because this is very important. Case number 1. Suppose you have two identical capacitors. What exactly that means? That means C1 is equal to C2, and let's say that's equal to C. That means you are connecting those two capacitors, those two parallel plate capacitors, whose capacitance is same. So in that case, when the capacitance is same, you tell me what will be the common potential in that case. You see, C1 it is C, C2 it is C, it will come common, C plus C, it will be twice C, C and C will go. I'm sure you understand that the common potential will be simply V1 plus V2 divided by 2. That means it will be the mean of two potential differences of your two parallel plate capacitors. V1 plus V2 divided by 2. We are talking about the case when the two capacitors are identical. Number 1, number 2. Second, what will be the amount of heat dissipated in that process? Right? What will be H equal to? It will be 1 by 2 C1 C2. It will be C into C, that is C square, divided by C1 plus C2, that will be C plus C, that will be twice C. Right? C and C will go. I'm sure you understand it will be 1 by 4. It will be twice C. C and C will go 1 by 4. C into V2 minus V1 whole square. This will be the amount of heat dissipated in the process when the two capacitors are identical. Capacitances of the two capacitors is same. That's my case number 1. Maybe you will require it somewhere. That's case number 1. Let's move to case number 2. Case number 2. And this case is very common in your competitive examination. You'll find a hell lot of problems asked on this case. That is, two identical capacitors. Two, again, same as that above. Two identical capacitors. You have two identical capacitors, right? But But that means actually C1 is equal to C2 and that's equal to, let's say, C. Right? C1 equal to C2, that's equal to C. But one of them is uncharged. One of them is uncharged. One of them is uncharged. Let's say V2. That means V2 is equal to 0. And V1 is equal to, let's say, V. I'm talking about the case when you have two identical capacitors, C1 is equal to C2, that's equal to C, and one of them is uncharged, that is V2 is equal to 0. Alright, in that case, what will be the common potential and what will be the amount of heat dissipated? Alright, let's see, check it here. What will be the common potential? V will be equal to, right? Again, they are identical capacitors, that is C1 equal to C2. Again, you will get V1 plus V2 divided by 2. But since now V2 is equal to 0, now the common potential, let me call this as V naught. Now the common potential will be equal to V1, that's equal to V naught, plus V2, that is 0, divided by 2. What exactly that means? Do you understand that? What exactly that means? If you have two identical capacitors, one of them is uncharged, then you connect them together, then the common potential will be half of the potential of first charged capacitor. That's V naught by 2. That's number one. Number two, what will be the heat dissipated in this process? H, that will be equal to. Since capacitance is again same, it will be 1 by 4C into V2 minus V1 square. V2 is 0, V1 is V naught. It will be 1 by 4 C into V naught square. Now this will be the amount of heat dissipated in the process in the case when you have two identical capacitors and one of them is uncharged. That is, the potential of one of the capacitors is equal to 0. Now let's talk about one more case, and that's third case. You have two capacitors. In fact, to be more precise, two different capacitors. That means C1 is not equal to C2. In that case, right, you have two different capacitors, not identical. Mind it, C1 is not equal to C2. But one of them uncharged. Let me say that V2 is equal to 0. And let me say that V1 is equal to V naught. Now again I'm asking what will be the common potential and what will be the heat dissipated. In that case, the common potential V will be equal to V1 C1 V1 plus C2 V2. Check it now. Divide by C1 plus C2. This is the common formula for the common potential. But V2 equal to 0 and V1 equal to V naught. In that case, you see what will be this equal to. It will be, let me write it again now here. It will be C1 into V naught divided by C1 plus C2. You have two different capacitors, but one of them is uncharged. Common potential C1 into V naught divided by C1 plus C2. Number one, what will be the amount of heat dissipated? H will be equal to, check here. It is actually 1 by 2 C1 C2 divided by C1 plus C2, V1 minus V2 whole square. Now you have two different capacitors, but one of them is uncharged. Heat dissipated will be 1 by 2 C1 C2 divided by C1 plus C2 into V naught square. Because V2 is 0, V1 is V naught, so heat dissipated in the process will be equal to this thing, right? So this will be the amount of this common potential and this will be the amount of heat dissipated in the process. But here again, I want you to have a look at these cases again, but because these cases are gonna be very, very important. That is normally, this is the equation for the common potential. This is the equation for the heat dissipated. I am now talking about the scenario. You have two identical capacitors, means that the capacitance of both the capacitors is same. Common potential, simply mean of the two potentials. Heat dissipated 1 by 4 C V2 minus V1 square. Number 2, very important case. If you have two identical capacitors, but one of them is uncharged, in that case, common potential is half of the potential of charged capacitor, right? Heat dissipated 1 by 4 C into V0 square. I'm sure that you understood it quite well, because this is very, very important. And then we have one more case here. When you have two different capacitors, but one of them is uncharged, right? So in that case, what will be the common potential and what will be the heat dissipated in the process? So I'm 100% sure that you will have understood these last 2 points particularly very well. Now, if you have done that, let's move to now questions. Let's talk about few questions here. Let's begin with this very, very simple question. All right, let's read the text. Let's read the text. Have a look. The question is, two conducting spheres of radius 6 centimeter and 12 centimeter, each having same charge, that is this thing. If they are connected by wire, find number 1, the direction and amount of charge transferred. Number 1. Number 2, final potential of each sphere. That actually means common potential. I will picturize this question. Let me picturize this question. You have a sphere. You have a spherical conductor here. The radius is given. R1 is given. R1 is equal to 6 centimeter. The charge is given. Q1, I think, is T into 10 power minus 8 coulomb. Let me check it again. T into 10 power. Yes, absolutely. T into 10 power minus 8 coulomb. Then I have one more conductor here. Radius is R2 and R2 is given, I think that's 12 centimeter. Yes, absolutely. And the charge is same. Q2 is equal to T into 10 power minus 8 coulomb. This is the data. I picturize the data. This is the data. Now the question tells me, I connected these two conductors by a wire. I connected them by a wire. We understand that. When you connect them by a wire, there's a potential difference. Charge will flow. And when the charge will flow, the charge will be no more Q1, Q2. It will be Q1 prime and Q2 prime. When the charge will flow till they'll reach the common potential. We are supposed to find the common potential and possibly we may find the heat dissipated as well. But since we are not asking about the heat dissipated, so we will simply go for two things. One, the amount of charge transfer and the direction as well. And 2, what will be the common potential? Now check. After connecting. Right? Now can you tell me, before you connect them, what's the total charge on the two spheres? Obviously, it is equal to Q, that's equal to Q1 plus Q2. It is same, 3 cross 10 power minus 8, 3 cross 10 power minus 8. So total charge will be 6 cross 10 power minus 8 coulomb. So if I have to find, let me first find the final charge on the both conductors. Let me find Q1 prime. That means the final charge on this conductor. That will be equal to total charge, that's Q, into radius of that sphere, that's R1, divided by sum of the two radii, R1 plus R2. Alright, I got the total charge already. So I will put the values here. I will get 6 into 10 power minus 8 into R1, that is 6. That's per centimeter. I'm asking you, do I need to change the units? Absolutely not. Why? Because in the denominator there's also radius. That will be also in centimeter. So centimeter will go. I don't need to change the units. So I will write simply into 6 divided by R1 plus R2. That is 6 plus 12. That will be 18. Alright. So that will be 6, 1, 6. 6 3 is 18, 3 1 is 3, 3 2 6. So that means the final charge on this sphere Q1 prime will be equal to 2 into 10 power minus 8 coulomb. Let me tell you now, I do not need to find the final charge on this sphere. You know why? The reason is, what was the initial charge on this sphere? 3 cross 10 power minus 8. What is the final charge on this sphere? 2 cross 10 power minus 8. What has happened? Has charge decreased or increased? obviously decreased. How much? 1 into 10 power minus 8. And why that goes? Why does that 1 into 10 power minus 8 coulomb goes? That goes here, which means that Q2 prime will be equal to what was initially 3 into 10 power minus 8. How much has come from this to this? 1 into 10 power minus 8. So what will be the charge? It will be 4 into 10 power minus 8 coulomb. So the final charge on this sphere is 2 cross 10 power minus 8 coulomb. The final charge on this sphere is 4 cross 10 power minus 8 coulomb. So what's the direction of flow? The direction of flow is from this sphere to this sphere. And what is the amount of flow? I call the delta Q. Delta Q will be obviously 1 into 10 power minus 8 coulomb. That is the amount of charge that has transferred. Now, sometimes you may have seen, I have written down all the equations here. Sometimes when you read the question, when you understand the question, you don't need to be so butch. You don't need to rely on equations everywhere, right? Sometimes things can be solved logically as well. That is a simple logic I used here. That if the charge on here is 2 into 10 power minus 8, it will be obviously 4 into 10 power minus 8 on the other side. And that actually means charge has flown from this to this. How much? 1 into 10 power minus 8 coulomb. That was the first part of the question. Let's move to second part. What is the final potential of each sphere? Right? What is the common potential actually? After connecting, what will be the common potential of both the spheres? Or you may call it final potential on each sphere. See. That I again come back to my point. Sometimes you don't need to rely on equations every time. Right? Why so I'm saying this? See. I calculated the final charge on this sphere. That's Q1. Where is it? It's Q1 prime. That's 2 into 10 power minus 8, right? If I had to find the final potential, I have the final charge, I will divide it by the capacitance. I will simply get the final common potential, right? If it's understood, let's try to rely on equations only. Have a look here. I need common potential. V. I told you that it's total charge divided by total capacitance. That means it is Q1 plus Q2 divided by C1 plus C2, or C1 V1 plus C2 V2 divided by C1 plus C2, which the equations which we wrote earlier. But now what's Q1 plus Q2? Is a total charge. You already know total charge is equal to, 6 into. It is 6 into 10 power minus 8 coulomb. Because each sphere carries a charge of 3 into 10 power minus 8 coulomb. So both will carry 6 into 10 power minus 8 coulomb divided by capacitance. Check. Capacitance of this sphere. It's a spherical capacitor. It's an isolated sphere. What's the capacitance of this sphere? What is C1 equal to? C1 is equal to 4 pi epsilon naught R1. I'm sure this equation should be fresh with you. What about this one? C2, that will be 4 pi epsilon naught R2, right? Because they are isolated spherical conductors. Their capacitance is something which we derived actually initially in the first part of the lecture, right? So I will write divided by C1 plus C2. It's 4 pi epsilon naught R1, 4 pi epsilon naught R2, right? So it will be, I can get 4 pi epsilon naught out, and then inside I will get R1 plus R2. R1 is 6, R2 is 12. It will be 6 plus 12, 18 centimeter, but I will convert it into meters. It will be 10 power minus 2, right? So moving ahead, solving it, putting the values, I get 6 into 10 power minus 8 divided by 18 into 10 power minus 2, and then there is 1 by 4 pi epsilon naught. You all know that it's 9 into 10 to the power 9. 9 into 10 to the power 9, right? Now check. 9 1 is 9, 9 2 is 18, 2 1s, 2 3s. All I get here is 3. Then 10 power 9, 10 power minus 8, it's 10 power 1. 10 power 1, 10 power minus 2 is in the denominator. It will go up 10 power 2. 10 power 2, 10 power 1, that's 10 power 3. That's 1000. 1000 into, or I will write it like this, 10 power 3. Not a big deal. I'm sure this is a simple calculation. Addition, subtraction, multiplication, and all of the things. So that means the common potential is going to be 3 into 10 power 3 volt. That means it's equal to 3000 volt, and that's going to be the common potential. How simple this is, provided you understand the basics very well, right? Moving to next question here. Moving to next question here. Now check here. You have got two capacitors. Here you have two capacitors. Check. Let's say this is positive plate, this is negative, this is positive, this is negative. Capacitance is given, potential is given, capacitance is given, potential is given. You are connecting them. Positive with positive, negative with negative. And after connecting them, question asks me, what is the potential on each sphere? What is the potential on each sphere? Which means that I am supposed to find the common potential. That's number one. Number two, final charge. We all know that. And then last one, heat dissipated. Right? Now it's only about using the equation. It's only about using the equation. Common potential. I will write down the equation. I'm sure that you will understand. Now I leave putting the values into it for you. That will be a kind of assignment to you. Like I'm supposed to find the common potential. Common potential V will be equal to C1 V1 plus C2 V2 divided by C1 plus C2. You see all the values are given here. You got to put the values here. That common potential. 1, 2. While you get the common potential, now that is what I want you to do. While you get the common potential, so that is you got that after connecting, what will be the potential of each capacitor, right? You have to find the final charge. Final charge you will get as final charge is equal to capacitance of the capacitor into common potential or into final potential, which is actually the common potential. So you don't need to rely on that equation that final charge is equal to total charge into C1 divided by C1 plus C2, which we wrote earlier, right? Now it is simple. You got the common potential. You are going to get the final or common potential you call it, or you may call it final potential. So final charge you will get the common potential into capacitance, common potential into its capacitance. You will easily get the final charge, and then we have heat dissipated. I already gave you the equation. H is equal to 1 by 2 C1 C2 divided by C1 plus C2 into V2 minus V1 whole square. Again, it's a matter of putting the values here. You have got all the values here. Just put all the values here, you get the answer. I leave this question to you. All you need to do is that, solve it and get the values. You can take a screenshot here. All right. Moving to next question. Now, these are few of the asked questions, right? Few of them are asked questions. In fact, this one is asked question. Have a look here what this question is all about. Question. A capacitor of capacitance C equal to 900 picofarad. You know that pico is 10 power minus 12. Is charged full by 100 volt battery, right? The battery is disconnected, and this capacitor is connected to another identical uncharged capacitor. The energy stored by the system is very simple, not a big deal. Let me picturize this question actually. You have a capacitor here. Please have a look here. You have a capacitor here. The capacitance is given, that's equal to 900 picofarad. That's 10 power minus 12 farad. That's the capacitance of this capacitor. You have connected this to a battery. That is, the battery has a potential of V. That is the potential of this capacitor. V0 will be equal to 100 volt. So that means this capacitor is charged. The potential of 100 volt. Capacitance is given. Now what you are doing is that you are connecting this charged capacitor with an identical uncharged capacitor. That means another capacitor is uncharged but identical, means the capacitance of that capacitor is also 900 picofarad. And then the question tells me that what will be the energy, stored by the system. So situation goes like that. So that means, let me show it here. You have one more capacitor. Capacitance is same, 900 picofarad. And that means 900 into 10 power minus 12 farad. Potential is 0. You see? Because it's uncharged. Now you're connecting them, positive with positive, and negative with negative. Now when you're connecting them, what will happen? Right? You connect them. This is your one capacitor. This is your another capacitor. It's very simple. You got to go back to the cases. You have two identical capacitors. One of them is uncharged. This is uncharged. Mind it, mind it. This is uncharged. You connect them together. If I ask you, capacitance will not change. It will be C equal to 900 into 10 power minus 12 farad again. It will be capacitance will be again 900 picofarad, 10 power minus 12 farad, right? Let me go back. Let me take you back to the case. Let me remind you something what exactly I was talking about. Let me exactly tell you what I was talking about. Have a look here. Yes, these are the cases I wanted you to remember. Two identical capacitors, capacitors same. One of them is uncharged. That is V2 is 0. One is V1, that's V0. Then the common potential is going to be V0 by 2. Number one. Number two, heat dissipate is going to be 1 by 4 CV0 square. Come back to this thing. Come back to this thing. Yes. Come back to this thing. Yes. Now. Identical capacitors, one of being uncharged. When you connect them, the common potential is going to be half of this potential. That means if initially it was V0, here it will be V0 by 2. Right? And obviously that will be equal to 50. Here it's going to be V0 by 2. I understand. I hope you understand it. I hope you understand this, why from this concept comes actually. Let me call this as V now. V is equal to V0 by 2. V is equal to V0 by 2. Right? Common potential is going to be V0 by 2. Now the question tells me, what is the energy stored? Obvious, not a big deal. It's obvious. Capacitance C. So energy stored 1 by 2 CV square. Capacitance C. Potential V 1 by 2 CV square. Right? So energy stored, 1 by 2 CV square plus 1 by 2 CV square, that will be simply CV square. But what is V equal to? That's V0 by 2. Energy stored by the system will be equal to C. V0 square by 2 whole square, that will be V0 square divided by 4. Now it's a matter of putting the values here. So what are the values here? So my energy stored by the system is CV0 square divided by 4. My energy stored is C is 900 picofarad, 10 power minus 12. Potential is 100. That means 100 square will be 10 power 4. 100 is 10 power 2. Square 10 power 4 divided by 4. Right? You put all the values here, or you may write it as 9 into, let me a little stretch it, 9 into 10 power minus 12, it will be 10 power minus 10. Right? Because I skipped these 2 zeros, so it will be 10 power minus 10. 10 power minus 10, 10 power 4, it will be 10 power minus 6 divided by 4. So your U will be 2.25 into 10 to the power minus 6 joules. This is the amount of energy stored by the system. I'm sure that you understood it quite well. Not a big deal. Not a big deal. This is the amount of energy stored in the system. Moving to next question. Have a look here. Question asks me, two identical capacitors, identical, mind it, it should hit you the moment you read it. Two identical capacitors, each of capacitance 5 microfarad and charged at potentials 2 kilovolt and 1 kilovolt respectively. They are connected together. Find the loss in energy. All right, have a look here. These are all asked questions. These are all previous year questions. You have one capacitor here. You have another capacitor here. They are identical. The capacitance of each capacitor is 5 microfarad, 5 into 10 power minus 6 farad. It's again here 5 microfarad, 5 into 10 power minus 6 farad. The potential of this is V equal to 2000 volt, 2 kilovolt. That means 2 into, I call this as V1, 2 kilo 10 power 3 volt. It's V2, it's 1 kilovolt. It's 1 into 10 power 3 volt. You connected them. Positive with positive, negative with negative. Question asks me, what is the amount of heat loss? What is the amount of heat loss? Remember, remind yourself, when you have two identical capacitors, capacitance is same, they are connected, heat loss is equal to, H is equal to, I'm sure you remember, it's 1 by 4, remember, 1 by 4 into C, into V2 minus V1 whole square. Hope you understand. Hope you remember. Hope you can recall this right from this equation comes. So heat dissipated at is equal to 1 by 4. 5 microfarad. What's C? Yes, it's 5 microfarad. It's 5 into 10 power minus 6. All right, into V2 minus V1. Okay. Or V1 minus V2, doesn't matter. Whichever potential is more, so we'll write that way. V1 minus V2 or V2. Because in the end, it's again square. It doesn't matter. If it comes out to be negative, it will square. It will again become positive. So 2 into 10 power 3 minus 1 into 10 power 3. It will be 1 into 10 power 3 square. It will be 10 power 6. It will be 10 power 6. So 10 power minus 6, 10 power 6 will go. It will be 1. It is 5 divided by 4. Heat dissipated is 5 divided by 4. That will be 1.25 joules. It will be 1.25 joules. That's answer to this question. I'm sure that you understood it quite well. All right, moving to next question. One more question. Have a look here. If you want to take a screenshot, you can take a screenshot as well. Yes. Do it fast. All right. Okay. Now we have another question. Two identical capacitors C1 and C2. Mind it, C1 and C2 are identical. Means I can keep them both as C. Of equal capacitance are connected as shown. Okay, this is C1, C2. I call them as C and C. Terminals A and B of key are connected to charged capacitor C1. Okay, there's a battery of potential V. The key is connected between A and B. Means battery is connected to C1. It is charging your C1. All right. Using battery of voltage, V voltage. Now disconnecting A and B. You are disconnecting this key here, right? The terminals B and C are connected. Means you are disconnecting key here and connecting B and C here, right? What will be the percentage loss in the energy? Again, this is P by Q. Now don't tell me, sir, it's frightening. We have done it already. Now let's try to decode this question. Let's try to picturize this question. Now what this question tells me. Have a look here. This is open on this side. B and C are not connected. That means initially this is not the part of the circuit. You have this capacitor, whose capacitance I suppose is equal to C. This also equal to C. You have capacitor C connected with voltage, with battery of voltage V. That means this voltage V will go to this capacitor, that's C, right? So it will be having a voltage V. So that means by connecting A and B, you are charging the capacitor C1 having voltage V, right? Now you are disconnecting this. Since the capacitor is already charged at a potential of V. Now you are disconnecting A and B and connecting B and C. So by connecting B and C, you are connecting C1 with C2. What do you understand? Isn't it same? Isn't it like this? I'm sure you understand. You have first capacitor connected to a battery of potential V. Connected to a battery of potential V, right? It will get a potential V. Capacitance is, let's say, C, right? That's what I'm talking about. A and B are connected. So that this capacitor is connected to a battery of potential V. Capacitor will get a potential of V. So you have a capacitor having potential V, right? Now, there's another capacitor, which is not initially the part of the circuit. Means the capacitance again is C, right? Capacitance again C, but the potential is 0. Potential is 0. All right. Now you are connecting B and C. That means you are connecting this capacitor with this capacitor. You are connecting these two. Question tells me what will be the percentage heat loss. Right. Initially, this is uncharged. There will be no heat stored. This is charged. So all the energy will be here, and that will be equal to 1 by 2 CV square. But once you connect them, right, there will be heat loss. So after connection, mind it again. After connection, what will happen? Have a look here. Again, initially, you have this capacitor having potential V. This is not charged. There is no potential. All the energy is carried by this thing, right? This capacitor. So the energy of the whole system is only energy of this capacitor. That's 1 by 2 CV squared. This does not store energy initially. Now you connect them. After connection, there will be heat loss. How much will be the heat loss? It is equal to 1 by, since they are identical capacitors, 1 by 2 C1 C2 divided by C1 plus C2 into V2 minus V1 whole square. But since when they are identical capacitors, it is 1 by 4 into C into V2 minus V1, that will be V minus 0 whole square. So heat lost is equal to 1 by 4 CV square. 1 by 4 CV square. What's the amount of heat loss? It is 1 by 4 CV square. All right. Now, understand one thing. What was the total initial energy? It's 1 by 2 CV square. What is the amount of energy lost? It's 1 by 4 CV square. Can I put it like this? The amount of heat lost is equal to total energy, that's UI. Sorry, I will write it like this. 1 by 2 CV square. Does it make any difference? Absolutely not. But you tell me, what is 1 by 2 CV square? That's initial energy or the total energy of the system. So can I say then, heat lost is equal to 1 by 2 total energy of the system? Then how much percent of energy is lost? Total energy was UI. Amount of heat lost is 1 by 2 UI, 1 by 2 into UI. How much percentage of energy is lost? Absolutely, you got it right. It's 50% of the energy has been lost. 50% of the energy has been lost. I'm sure that you understood this question. If not, think again. I'm sure that you have that capacity to think again. Right? Since the total energy initially was carried by only this capacitor as 1 by 2 CV squared, this was not carrying any energy. Amount of heat loss is 1 by 4. I broke it. 1 by 2 CV squared. 1 by 2 CV squared is initial. So heat dissipated is half of U initial. So how much, what's the percentage of energy loss? That's obviously 50%. I'm sure that you understood it quite well. So this is some part of your capacitors. We are left with few more part, but we'll be taking care of that in the next session, right? I'm sure that you understood it quite well. I would have loved to solve more and more problems, but we'll be doing in the upcoming sessions as well. But for that, you need to subscribe to Unacademy CUET English if you have not subscribed it yet. I will see you in the next session. We'll be completing the capacitors hopefully in the next session. Till then, just take good care of yourself. I'll be signing off as of now. Bless up all and love you all.